Welcome back, everybody. So let's continue our journey on OLTP and OLAP. And again, I finished by saying it's getting blurry between the two because now a lot of systems try to do both. The hugely parallel systems on the OLAP, so read-only, are slowly going into the updating sites with the Delta Lake, Apache Iceberg, and so on. So it's getting common. And OLTP is also increasing use for OLAP. So we have this HTAP. By the way, fun fact, Marcus Pillman, who was the president of FIS 18 years ago, I think, wrote his PhD thesis exactly on that. So this is, you can look it up. I think it was called TEL. That's an elastic database system for mixed workloads was the name of the thesis. So that was here at ETH. All right, so let's just quickly talk a bit about OLTP versus OLAP to give you an intuition. It's a lot by contrast, right? So OLTP, that's the day-to-day business of the company. It's the suppliers, it's the customers, it's the orders, it's the inventories, it's everything that's going on with millions or billions of updates per second, right? You have a business going on, that's the day-to-day business. OLAP is the data analytics for what goes to the C-level executives of the company, CEO, CFO, CTO, the board of directors, so for the decisions. And so this is what happened in the 1990s, 1995, that a few startups got created with the goal of freezing some data and then analyzing it to provide these super fancy reports to the C-level executives. So it's read-only. Typically, you just read and you analyze the data as it is, right? So as a consequence, typically OLTP is associated with a lot of writes. OLAP is associated with a lot of reads, and maybe even only reads. So think for OLTP in what we studied this semester. Think of MongoDB, of PostgreSQL. You know, this is all on the OLTP side. And MapReduce, Spark, the data lakes where you just drop your data sets and don't touch them because there's no write random access. This is all OLAP, right? Who is with me? Right? Very good. So OLTP, lots of writes. OLAP, lots of reads. OLTP is a lot about detailed individual records, right? Because, why? Because you have customers connecting to your website. So you want to access the customer records of whoever is connected to your website. They're ordering items, so you want to access the particular records corresponding to the items that they're ordering. You want to access the very order that they are placing, right? So it's individual records for the day-to-day business. For OLAP, you want historical, consolidated, summarized data to build fancy reports that C-level executives will love, like looking just like what you have on the right? So you want to consolidate the data to provide these fancy pie charts and plots on the high level over the whole database. So it's going to be a lot of aggregation queries. Then a consequence of that is that when you have an OLTP query, you're going to have a lot of point queries, a lot of the updating queries that modify just one record. So you look, it's like a Tetris game, if you want to remember that in this way, but you're looking at small portions of the data. But in OLAP, you're looking at very large portions, the entire database. You might join the data, even though we are scared of joins, so we try to pre-compute the joins by denormalizing the data, right? But you can't always do that because sometimes there are many ways to join and you cannot pre-compute them all. So you're going to have a lot of very heavy queries, group by, join, and so on, very expensive that might even last a lot of time, right? So this is why on the OLTP, typically less than a second, very often even a few milliseconds. Nowadays, if you want to look up a record among billions or trillions, it's less than 2 milliseconds with indices, right? We've seen indices a few weeks ago, right? Hash indices, B+3 indices. So that gets you instant lookups for point queries because you're looking at specific parts of the data. OLAP is from slow interactive to very long-term, not even interactive anymore. So an OLAP query can be overnight. You come back on the following day. You know, just like MapReduce, I told you it can be several hours until it computes. So it's absolutely not interactive. You have to go home and come back on the following day. There is, though, what is called slow interactive, where it's a few minutes. A typical way to visualize this of the sort of products we had in the 1980s is that some people that are not necessarily computer scientists, might use Excel or a spreadsheet software that they connect to an OLAP system that is running on some server, and they put a query, and maybe it's going to take a few minutes until it's loaded and processed and appears in the spreadsheet, right? So this is slow, interactive, right? So not immediate, but a bit slower. And again, you imagine why. This is why. This is because the queries involved are not just point queries where you just look up an index. You might have group by, you might have join, you might have to scan the data in order to achieve that. Next, this is something that I'm repeating because I think I said that the whole semester. In OLTP, the good old databases from the 70s, we are very excited about the normal forms. We love the first normal form, atomic integrity, the second normal form, the third normal form, the 3.5th normal form known as Boyce code normal form, the fourth normal form, the fifth normal form, the sixth normal form. We are obsessed with normal forms. This is why we teach them to you at the bachelor's level, because when you write a lot of data and you constantly update the data, you don't want anomalies. And the normal forms protect you from anomalies. So you want to make sure there's no duplicates anywhere and the data is nicely structured to facilitate updates. However, when you want to analyze the data, you don't modify the data, it's just the way it is. Then you throw away the normal forms. You go all the way down to the first one and maybe even below the first, maybe even not even first normal form. What that does is that it creates a lot of redundancy. But we don't care about the redundancy because we don't have updates anyway. And the redundancy makes it quicker to query because we don't have to join the data anymore if it's already pre-joined, right? So there is this contrast between a lot of consistency for OLTP, a focus on consistency, and for OLAP, redundancy. And that includes redundancy with the replicas of the blocks in HDF and so on and so on. We just replicate things like crazy, right? Who is with me? Right, very good. So I'm just associating things, right? I'm just associating a lot of contrasting properties with the two. There's even more, I'm not going to talk much about that. It's just even more contrast between OLAP and OLTP. Maybe I can, the backup one, the OLTP system with the day-to-day business, you want to back that up. OLAP doesn't really matter or matters less, at least for the business analytics, because it's derived data. So if you lose it, you just recreate it, you just re-import it, right? I'll say more in a bit, right? Anyway, and you see normalized tables for OLTP, but you can denormalize things in OLAP because it's read-only. Okay, you can take a look at that offline, all of this. I'm not going through these ones, but this is just some additional ways that you can contrast them. Okay, so this is OLTP versus OLAP. So now let me say a few words about these new systems from the 1990s that were built by a few startups. These systems for business analytics were born with 4 adjectives that qualify them and that you will find in a lot of OLAP literature. It's, look at the title of the slide, subject-oriented, time-variant, non-volatile, and integrated, right? So let me talk about these 4 quickly. Subject-oriented means that the business analytics typically has a very concrete use case. The number one concrete use case for business analytics is the sales data of the business, right? How much are you selling? And you aggregate over the years the sales and so on to see the performance of the company. But you can also do it with web analytics, right? The visitors of your website. You can do it with census data that is perhaps the oldest use case of modern computing. IBM actually dates back to that. It's very, very old IBM. And that was actually dating back to the census in the US, where you needed to gather and aggregate data. It was even before the silicon processors. That was mechanical machines that were built at first, right? So the census data was one of the very first use cases of this. Science at CERN, for example, all the data you gather from the LHC collider, Large Hadron Collider, LHC, and so on, right? So subject-oriented. Second, time variant. Time variant just means that we are very aware of time, in the sense that when you run the day-to-day business of the company, you have the current snapshot of the data, and you just keep updating it, but it's always the current data. In OLAP, it's different. You like to have the past data from the past few years, typically all the way to 10 years back, right? So where you have the data, and then you want to analyze the data over this time. You like these fancy curves that show the evolution of the revenues of the company for the past few years or the past few quarters, right? So time is very important. It's rare that we go back more than 10 years in practice. If you talk to people in companies, there's many reasons for that. It's maybe less relevant because it's too far away in the past, or maybe the shape of the data, the schemas are so different that the costs of using them would be very expensive if you use traditional systems, because if you use schemaless systems like JSON and so on, you don't have that problem. But anyway, typically 10 years back in the past. Even though there was at some point a continuing education student a few years ago who shared experience to the class with their own company, they were saying that they pushed the data gathering all the way to the basements to find the paper blueprints of the building to know where the water pipes were, right? So this is saying that you can go back to, some people like to go back very, very far away in the past. I think from 100 years ago was the order of magnitudes, and so on. All right, so time is very important. We do want to have the data over time. The next one is non-volatile. This one is very easy to explain. You just don't modify the data. It's frozen. You import it. It's the way it is. You just read it and analyze it, right? So you load the data, and that's it. You access it. Non-volatile. And the last one is integrated. And the idea of integrated is that the system, the OLAP system, typically called the data warehouse. I think I haven't said the word yet. It's a data warehouse that you want to have for these data analytics. It belongs to the ecosystem of your company, right? So what do you have typically in a company? You have the enterprise resource planning, HR, finances, you know, the rockstar advertisements and so on. CRM is customer relationship management, Salesforce and so on. OLTP would be your, you know, the inventories, the orders, the customers, and so on. Some companies, you wouldn't believe the number of companies whose data is literally in Excel on the local drives of the employees. You wouldn't believe, but this is real and very inefficient. But this is the real life, and so you have also data that is in there. People actually go as far as to print the spreadsheet, send it over mail, and then the other side, somebody opens the envelope, retypes it into a spreadsheet, and there you go, right? You can imagine all the errors that get introduced. But again, we are working on digitalization and on these things, right? So these are the systems that we have in the company. This is where the data, the OLTP data, typically is. So what we want to do is analyze that data. So at first, you might think, okay, imagine you're hired by a company, they ask you to analyze the data. You request the password to connect to the OLTP system, and then you run a query that aggregates everything. What's going to happen is that within a few hours, you're going to get a lot of people knocking at your door, like, what's going on? What are you doing? You know, you're slowing down the whole system. The company is stuck because of your query that is just weighing heavy on the system. So you don't do that. You cannot directly query the original databases. Instead, what you do is that you carry over the data to some other place called the data warehouse, preferably during the night or during the weekends when nobody is using the data. So you carry it over, that's called ETLing, to your data warehouse, which can also be referred to as materialized views, right? You import it in there, and there you have your data cubes, as we will see. You can analyze, build reports, mine with machine learning, because your data is very clean. So I put as an analogy, the wheat, the flour, and the bread to just see the levels of transformation, right? ETL is an abbreviation that I have already mentioned, which means extract, transform, load, exactly. And this is where consulting companies make millions of dollars. Because you need to connect the gateways across, you know, the OLTP system, the OLAP system, automatic imports. You might extract with Hadoop from the logs. There's plenty of software for that. You might have triggers. Maybe you don't want to re-import the whole thing every time, so you want incremental updates where you just push what is very recent. In fact, there's a lot of new software, recent software that is streaming, where you only look at the increments, at the data modifications, and not at the whole data. Once you have established the bridge with the classical systems of the company, traditional systems, you need to transform the data. You might need to throw away some data you don't need, to filter it. You might need to clean it up. You wouldn't imagine all the work that goes. Ask anybody who does machine learning and ask them what % of their time they spend cleaning up the data versus actually training it. So absolutely fundamental. So this is the transform part. And then we load it into the system. The system, just like MongoDB or PostgreSQL, they have their own internal format to store. So they might have indices made to optimize the queries on the data cubes. They might partition the data. They might have integrity constraints and so on and so on. So you load it into your system, right? So this is ETL. So before we get to the actual interesting part, I'm not saying this is not interesting, right? But the coolest part is when you look at the data model. I want to mention that historically there were these startups, Sbase, Cognos, and so on, created in the 1990s. Then something happened. There was a market consolidation where the big players, you know, IBM, Oracle, Microsoft, they wanted their share of the market, of course, because everybody wanted to do business analytics. And then they figured out that data cubes, so the sort of business analytics that they are doing, can very naturally use as a physical layer, data independence, physical layer, a relational database management systems. In other words, you can store a cube on top of a table. And because they realized that, all the big players that had relational database management systems, they thought, let's do business analytics too. So Oracle bought Sbase, IBM bought Cognos. Microsoft, I'm not sure if they bought anything, but they have these analysis services that does the equivalent. I should look again at the history of what happened there. And there's a fourth player, SAP, with SAP HANA, that is also in the ecosystem. So these are the players. I think that Sbase is still in use as a brand. Cognos is also still in use, but just as part of Oracle and IBM. Do you have a question?
By placing cubes on top of tables, you mean like inside them, or how?
I mean as a physical storage. Remember data independence? You have a logical model and you have the physical storage. For example, your logical model might be relational tables, and PostgreSQL stores them on top of the files on your hard drive. That's the physical storage. You could also have graphs that are your logical model, stored natively by Neo4j as files on the disk, right? Which is what it does. RDF, in the very early days of RDF, people were actually using relational tables with 3 columns to store the triples, right? It's very natural, a column for subject, a column for property, and a column for object. It's easier because then they can just reuse SQL as the physical layer. And what's very important to understand is that the relational table can be the logical layer if you're the end user analyzing tables, but it can also be the physical layer of another system built on top, right? So it's all a Lego game. It's all modular. So that's what I mean with that. But I will show you. I will show you what the tables look like for cubes. It's beautiful. You will see. Okay, any other questions? So far, very good. So let me move on. So now the coolest part, the data model. As every week, I give you the data model of HDFS first. I give you the data model for XML and JSON. I give you the data model for JSONic, the data model for label property graphs, and so on, before the physical implementation. So I'm going to do the same. Let's look at the logical data model for data cubes without worrying about how it's implemented. You know, just the logical model, the math, how we look at it logically. Maybe I should say quickly that the reason we look at data cubes is because historically, the OLAP systems, the analytic systems, were built on cubes, right? But now you could argue that OLAP is not on the cubes. You can also do OLAP on trees or on tables. In fact, you could consider that Spark is OLAP, right? But then the data is not necessarily cubes. But there is this association just for historical reasons, that the early OLAP systems were based on cubes, right? That was one of the former TA, head TA of the course, Ingo Müller, was really pushing for this, that OLAP is not just data cubes that can be any shapes. All right. So this is the logical model. It's a cube. A cube has dimensions, right? Typically, we visualize it as 3 dimensions. So imagine that I have my data and my 3 dimensions are a year and a kind of product, phone, TV, and so on, and a country, Switzerland, Austria, Germany, for example. What's going to happen is that for each combination of year, product, and country, I have a value. An example is the value 7, that is corresponding to the year. So that's this dimension, the year. So this is the year 2024. The products, that would be this dimension here. So the products here would be the servers. And the country, that's the dimension here, the depth, would be Switzerland. And the 2024 CH server is 7. Maybe the meaning of that is my company sold 7 servers in Switzerland in the year 2024. Right? But now you need to imagine there's numbers everywhere for other years, for other products, for other countries, right? For every combination, I have a value of how much of what I sold where and when. Okay? Who is with me? Right? So that's the cube. Now, we humans live in a 3-dimensional world, plus time, 4 dimensions, but 3 spatial dimensions. Just out of curiosity, whoever tried to visualize the 4-dimensional hypercube? Some of you, who manages to do that? There are people who do. Don't have any raised hands. There are people who manage to do this. It's very difficult because we just don't experience the 4th dimension. And yet, you have experienced it in your linear algebra courses. Because in linear algebra, nobody ever told you you cannot have more than 3 dimensions, right? You can have many. But it's just because of your abstraction skills that you were able to still do that. So what I want to say here is that even 3 dimensions was complicated to represent on a slide because that's 2 dimensions on my screen, but I could not represent 4. But in an OLAP system, you can have 4, 5, 10, you can have more dimensions, right? That's not a problem at all, right? Okay, so I wanted to say that is just for this example that I picked 3, but you can have more. Now, what kind of dimensions do we have? Well, you can have a geographic dimension, so the distribution by countries and regions and cities and so on. You can have a split by currency. Maybe you want to separate your revenues in dollars, in euros, in rupees, in yuan, Swiss francs. So you might separate the revenues from the profits, from the expenses, and so on. So it's basically what you're talking about. When you might want the years, the quarters, the months, the days, maybe the hours. So that's also a dimension. You might have who, for example, for your teams, if you have the sales data and you want different teams to compare the data, right? So these are possible dimensions of your cube, but there can be many, many, many different dimensions, right? It's even user-defined, so you can make up your own dimensions, right? These are also called axes by some communities. Now, coming back to the fact that it's very difficult to visualize a cube with more than 3 dimensions, it's good for the abstraction layer, right? When you design your logical data model, you think of the cubes in this way. But there is a way to make it a bit easier for us humans to look at in terms of the data. If you want to look at the actual data, there is another way. And here I'm referring to your very early childhood memories, perhaps even so early that you might not even remember that anymore if you were younger than 3 years old. But I'm sure that all of us, I surely did, at some point in our childhood played with these kind of cubes, and we love to take them and build towers of cube and try to make the tower as tall as possible, right? So let's call up these memories where you take all of these cubes, you just completely collapse the whole cube, cut the individual cells, and now you build a tower where you put the cubes on top of each other. Who is imagining that? Right? Okay. It's very ancient memories, but with a bit of effort, we remember. Do you agree that this is what you get? This is exactly what I described. I'm taking all of these little cubes and I'm piling them up. You see there's a little cube that had $1,000, which was located at Germany 22 Peter, another little cube below, and here I have 8 little cubes. Looking at this, can anybody tell me the dimensions of the original cube? Knowing that these are the coordinates, these are the dimensions where they were in the cube, and this is the actual value. What were the dimensions? Yes? So these are the dimensions and the size of the dimensions. So the length, the breadth, length, and depth of the cube. How many cells by how many cells by how many cells? Yes? Yes, exactly. Which are in this concrete case? 2 by 2 by 2. Yeah, so that's Germany, Switzerland 2 by 2, 22, 21 by 2, Peter and Mary. And 2 times 2 times 2 gives us 8, so that's good, right? We have all of the cubes. So this is a 2 by 2 by 2 cube that we've represented as a big tower with all of the 8 cubes, one on top of each other. Do you see that this is a relational table? This is called the facts table. This is the facts table that corresponds to the cube. So now we have this representation right here, that is the abstract one for the logical data model. And we have this physical representation as a facts table, as a relational table. But you have to see that this is physical. This is a physical representation of my cube. It's not the actual logical cube. Who is with me? Right. For whom is this a natural thing to do? Right, very good. So this is called the facts table. Now I'm going to tidy things up a little bit, as is done in the business reporting community, by adding a few bells and whistles to that facts table, so it brings a bit of terminology too. I told you the dimensions can be called axes, and sometimes we even put that in square brackets. Axis, 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 axis. The values of the dimensions, they are members, so members. We like to add that to clarify that these are members. And here it's special. That's just the value of each cell, the value of each fact, and then we have the actual values there. By the way, as part of the tidying up, I took the dollar in here and moved it over to a column of its own, right? Then it's 2 by 2 by 2 by 1, right? Just because it's dollars everywhere. But technically, it's commonly also stored as a dimension, right? But you could have also euros and other currencies. Who is still with me? Right. So this is a facts table, representation number 2 of a cube. And now you probably understand why the big players of the relational database management systems, Oracle, IBM, Microsoft, went after this market, because you can store all these cubes in their existing relational database management systems. So you can imagine the interest that there was. Now that we have the data model and we have the representation as a facts table, because for us humans, it's easier to look at the data in the facts table, we are going to start manipulating the cubes. If we manipulate relational data, what can we do? We can select, we can project, we can rename attributes, we can aggregate, we can sort. So this is called the relational algebra, right? Okay, so this is the relational algebra. So here we have a cube algebra. The cube algebra uses different terminology, different words. The first word is slicing. Whoever heard of slice and dice? Okay, so some of you, right? It's a buzzword, slice and dice, in this universe of business analytics. Let's start with slicing. It's very intuitive, actually, just like you take a slice of a cake. So here it's just a slice of the cube. You take a particular value for a dimension, and you just take just the slice that corresponds to that value, a particular year or a particular country. That's a slice. This is called slicing. Do you agree that this is the slice of my previous fact table here? Can any tell me what slice that is? How did I compute that slice? Can you figure it out? It's half of my cube, right? It's 2 by 2 by 2, and now I have 1 by 2 by 2. Yes? Exactly. I use the slice location equals Switzerland, and location equals Switzerland gives me a slice with just 4 cells, 4 facts left. Okay, so who agrees? Right, so this is a slice. Now, let's make the slice explicit, because you see Switzerland is constant. It's always Switzerland in location. right? It's always Switzerland, and here it's always USD. So let's move them over to here on the top, right? This is what's typically done in Vue. So these are my slicers. These are my slicers. I take only the facts that have this particular coordinate in my cube, and now I have 2 dimensions left. What is a cube with 2 dimensions? Primary school. So we were 3-year-old, now we go to primary school, yes? A square, exactly. This is a square. So now that, because we sliced, we have 2 dimensions left with distinct values, who feels the irresistible urge of displaying this as a square? Right? Like this. This is exactly what we call dicing, slice and dice. So we slice all the way that we have 2 dimensions left that vary, and then we slice it, we dice it by saying, let's put the salesperson axis on the rows, and let's put the year on the columns. And now I nicely get back these 4 values still piled up as a tower, and now I represent them as a square. For whom is that natural? Right? This view that you see here has a name. It's called a cross-tabulated view or a cross-tabulation. It's very natural for humans because this is the idea that we are very good at 2 dimensions. We look at a screen, we see 2 dimensions. A spreadsheet software is made of 2 dimensions. And so this is why we do it in this way. In fact, this is a feature that spreadsheet software has that is called a pivot table. Who has ever played with a pivot table in Excel? Right? So many of you, if you haven't, then you should try it. Right? This is really based on drag and drop. You drag and drop the dimensions to slicers, you select the values you slice, you drag and drop a dimension to the rows, you drag and drop a dimensions to the column, and then you get this very nice cross-tabulated view that looks like this, right? And it's really something you have to think of as interactive. You can drag and drop things and modify interactively the view. All right, so this is the cross-tabulation. So now we are at 3 different representations. We have the cube, very hard to visualize beyond 3 dimensions. We have the facts table. That is typically a CSV file that you download from the internet, right? It's in the form of relational data. You have plenty of files like that on probably the Federal Office of Statistics and so on. You have plenty of data that looks like this. And then with your spreadsheet software or with your fancy data analytics products that does it efficiently for you for very large cubes, you get these cross-tabulated views. This is how data cubes are queried. Now, I still have time, I think. Yeah, I can do a bit more. We had 2 dicers, right? And all the rest was as a slicer. 2 because 2 dimensions of the screen. You also have the possibility to have only 1 dicer, right? If you have only 1 dicer, then maybe you can put the dicer just on the rows and no dicer on the column. Then if I hide this, basically that's what you get when you have just 1 dicer, you just have 1 column. What you can also do, even though that's not typical, but you can also put the dicer here, then you have just 1 row, right? But this is a bit less typical. But this kind of dicer with just 1 column, you probably already saw that in whoever saw a balance sheet or an income statement, a cash flow statement, maybe if you're the treasurer or the questorin, right? So this is typical, right? The sort of views that you get. So this is 1 dicer. But typically balance sheets also is very often still with the periods, with the last year and the current year. So let me give that back to you. How can I remove it? Let me put it back. There you go. Thank you. So we can have 2 dicers, rows and columns. We can have a single dicer, or we can have 3 dicers. Does anybody see in terms of UI? So put your UX hat, so the user experience. If you were to design something like this that is intuitive, where would you put the 3rd dicer? That the depth, yes, but the screen doesn't have depth, right? So where could you put it in a UI, the depth? Sorry? Yes, that's it, multiple sheets, right? Exactly. So you could put the 3rd dimension as your tabs. right? In spreadsheet software, you have the tabs at the bottom. So you could put the third dimension, you select the value at the bottom, and that's your depth. That's basically how you do it in a user interface, right? So that's the idea, right? So that's correct, basically. Who is with me? All right. So 1, 2, or 3 dicers, all the slicers, we drag and drop stuff into place in the way we want to do it, and then the software nicely builds that cross-tabulated view for us. And all the rest goes to the slicers. So basically, whenever you build a view like that, you need to make a decision for every dimension. Do I want that dimension to be a dicer, or do I want it to be a slicer? Either or, right? You basically assign these properties. Let's look at another thing you can do with cubes. I'm not sure if that slide actually, maybe it's hard to see. Does anybody see what's going on that slide? Between the left and the right. Does anybody see it? Yes? Yes, the depth is merged. You see here, I have 3 layers in the depth, and here I merge them. By merging, I mean aggregation. Maybe I summed them over, or I counted them, or I took the mean, or I took the max, or I took the average, right? So whatever aggregation I have, I'm basically squeezing my cube like this, and I'm aggregating the values across the dimension in which I'm squeezing. So now I had 3 dimensions here, and I'm left with 2 dimensions because I aggregated my data. So let's do it on that example. So imagine that I want to squeeze this 2 by 2 by 2 cube, and I want to squeeze it according to the colors that you see here. I basically want to squeeze along the location axis. I want to aggregate my data, basically getting rid of the location. I add across the location, but I keep the period, I keep the salesperson, I keep the currency. So do you see that 1,000 gets with 5,000, 2 with 6, 4 with 7, and 4 with 7, and 3 with 7, and 4 with 8. Who sees that? Right, so this is exactly what you see pictured here, where the location axis would correspond to the depth, right? So this is the location, and I'm squeezing Germany and Switzerland in here, right? And I get this, because I did plus, right? So 1 plus 5 is 6, 2 plus 6 is 8, 3 plus 7 is 10, and 4 plus 8 is 12. So this is what I get. And now I replaced my location with the whole world. Imagine my company is only in Germany and Switzerland, and I can say the whole world is this data. Instead of member, I put domain, right? Because that's the whole domain, and that's why I also put it in a different color in here. Now, as we did before, since it's always one value in here for the location and the same value for currency, I'm moving them over to the top, right? So it looks like a slicer actually, but now the location is a slicer on the whole domain, right? So this is because I'm aggregating, right, with a sum. Now we have only 2 columns, so naturally we'll want to display it as a square like this, and this is another cross-tabulated view. And the difference with the previous one is just that my slicer is on the whole domain, right? The one in the dark purple. Who is still with me? Right, very good. Now, another way to aggregate while keeping the data is called subtotals and totals, right? So here it's the same view, but I'm adding here the subtotals. So I'm summing over the rows, I'm getting this plus this plus this. And I'm also having a subtotal here that is the sum over the rows, and a grand total at the bottom right of the screen, right? So this is also a kind of aggregation, but the difference is that in the case of location, I only kept the totals, I aggregated. Here I keep the individual values together with the totals, right? If I have a dicing dimension, I can do that. Who is still with me? Right, okay. Now, the dimensions have hierarchies, right? They are organized like this. For the world, it's natural, right? We have continents, countries, regions, cantons, Bezirke, districts, Gemeinden, and so on. Periods is the same. We have years, we have quarters, we have months, so you can also see a hierarchy in here. So there's the notion of dimension. For this reason, we have very nice visuals that we call L shapes for the columns. And you see how they work. It's really beautiful. You have here, let's say, Zurich, Geneva, Interlaken, aggregated to Switzerland. So I have this L here that says Switzerland. The total is here. Then Berlin and Frankfurt, Germany. Switzerland and Germany, another layer of aggregation. Europe, like here. Then I have, the slide is too small, so this is why I just put Beijing and Delhi, but this is, you get the idea, right? So the whole of India, the whole of China, the whole of Asia. Again, the slide is too small to include everything. And then the whole world, right? Who is with me? Right, so here, what you need to see is the L shapes. The visualization based on the L shapes clarifies that these are subtotals that get aggregated. The L shapes are commonly done on the columns. On the rows, you don't typically use L shapes. Rather, you use underline and bold and indentation, but it's basically the same thing as the L shapes, right? So it's the same thing, but transposed, right? I just transpose this thing, and then I get this instead. Right? So this, again, if you have done some accounting as the treasurer of an association, then you've seen these things, right? It's also commonly used in accounting, these things. So the balance sheet, the income statement, the cash flow statement, and so on, you can do them like this. So L-shaped on the columns, indentation on the rows for the hierarchies. Now let me show you something beautiful that's called a roll-up. Whoever heard of a roll-up? So a roll-up is like when you roll up the curtains, right? So imagine that I want to roll up because I'm no longer interested in the city level, so I just roll it up. Let's say I'm not interested in the country level, just the continent level, I roll it up. I'm not interested in the individual continents, I roll it up and I end up with this. That's called rolling up, right? And then you can even put the world as a slicer on top because there's only one left. That is an example of view with only one dicer. Right? The dicer is on the rows and there is no dicer on the columns. Who is with me? Right. The opposite is drilling down. If I drill down, I just add granularity. If I roll up, I remove granularity. That's the idea of how it looks like. And again, that only works because you have a hierarchy in every dimension that you're able to do this. Okay? Any questions so far? No questions? There's one over there. Yes, maybe we can bring the microphone or, yeah. Small hops, do not scare anybody.
Thank you. So is this only about the user interface? Because the operations that we are allowed to do are just a subset of SQL, right? And SQL wasn't so hard in the first place.
That's the next part. So you've just given me the excellent transition to tomorrow. So if you want the answer to your question, you come back tomorrow at 9 a.m. and we'll look at the implementation. Guess what? It's on top of SQL. So we'll write the SQL queries that give you the data that you can use to populate. But the user interface is part of OLAP. It's really the spirit that a lot of people use a front end to query the data in this way. So thank you for the question. That's the perfect way to end today's lecture. So come back tomorrow and we'll look at the SQL implementation of data cubes. Thank you very much and see you tomorrow.